So we've been talking about power series, and we found a couple of geometric power series that we could find out what their function converged to, or what the polynomial converged to a given function. And then we even found that we could take derivatives of those polynomials to get new functions, and we could take integrals, and we could even substitute some things in. Because the goal is to try to find as many functions that we can find power series for. But even with all those things we learned in the last talk, it still doesn't cover many functions. So we're going to try today to come up with a way of taking any function and finding a power series for it. Wouldn't that be kind of special? So this is what a general power series looks like. So all power series look the same. The key is finding out what these C's are. So what we're going to do is we're going to let f of x represent that power series, and then I'm going to take some derivatives. F prime of x, double prime of x, triple prime of x, the fourth derivative of x. I think that might be enough. So what is the derivative of this side? Derivative of C0 is 0, then you get C1, and the derivative of this would be 2C2 times x minus a to the first, plus 3C3 times x minus a squared, plus 4C4 times x minus a cubed. And then the second derivative, taking the derivative of this, you get 2C2 plus 6C3 times x minus a plus 12C4 times x minus a squared. Of course, all of these really just keep going. Then that goes away, so you get 6C3 plus 24C4 times x minus a. And then finally here we get 24C4. So the whole goal is to try to find out what these C's are. So what I'm going to do now is put into every one of these functions, I'm going to put in for x, I'm going to put in a. So f of a is going to be C0, and then everything else wipes out because you have a minus a. And then f prime of a, we get what? C1 plus everything wipes out. F double prime of a gives us 2C2. F triple prime of a gives us 6C3. And the fourth derivative at a gives us 24C4. So if we want to solve for these C's, I get C0 to be f of a, C1 to be f prime of a, and let's just make it over 1 factorial. C2 would be f double prime of a over 2. But let's just call it 2 factorial. C3 is f triple prime of a over 6, which we can call 3 factorial. And C4 equals the fourth derivative at a over 24, which I could call 4 factorial. So in general, what do I see? That C sub n is the nth derivative at a over n factorial. And you could even call this the 0th derivative at a over 0 factorial. And it even works for n equals 0. So what we have then is f of x can be written as the summation from n equals 0 to infinity. And now we know what these c sub n's are. There they are. They're the nth derivative at a over n factorial times x minus a to the n. And we've got a formula. And we can call this the Taylor series for the function f of x. And it's centered at x equals a. Because remember, we picked a to be different values. And the reason we say it's centered at a is because that's where it's going to approximate the best. Because we're never going to be able to take an infinite number of terms. So wherever we stop, everything that we miss out on is going to have a x minus a to the nth power in it. So the closer x is to a, the better the approximation is going to be. In fact, it's going to be perfect when you're right at a. F of a is going to equal f of a. So that's why we center it there. Now, since always, this looks kind of funny, this 0th derivative and 0 factorial. When I like to write them out, I like to just say f of a plus, and then just take the summation from n equals 1 to infinity. So either way, you can write it. They're really the same thing. And when you see them written out, what you have is f of a plus f prime of a over 1 factorial times x minus a to the first. And this keeps going until you get to the nth derivative. That same term right there, plus, and then you're going to have a bunch more terms, starting at the n plus first derivative. Well, this right here, the first n terms, because we're never going to be able to really find all the terms, we call the first n terms Pn of x. And that's called a Taylor polynomial of degree n. And then the part that we omit, all the rest of this stuff, is called Rn of x. And that's called the Taylor remainder. Basically, that's the error that we're going to have if we try to approximate the function f of x with just an nth degree Taylor polynomial. So that's all the terminology. Now, the Taylor series was named after an English mathematician, Blake Taylor. And he did this work in the early 1700s. So, we have some terminology. Now that we've got this formula, I think we should start to use it. So what function should we pick to do first? Well, for two reasons, I'm going to pick f of x to be e to the x. Because this was that function we came up with a power series that seemed to be e to the x, but we had no proof of it. And another thing is, this is going to be about the easiest one to get a Taylor series for, because what we really need in this formula is all these derivatives. And the easiest thing to take a derivative of is e to the x. You keep getting e to the x. Now, once you get all these derivatives, the next thing is to plug in a. So let's center this one at 0. So we say f of 0 is e to the 0, or 1. F prime of 0 is also going to be 1. In fact, for this particular function, e to the x, everything is going to be 1. F of a is going to be 1. All of these derivatives are 1. So what are you going to get? You're going to get 1 plus the summation n equals 1 to infinity of 1 over n factorial times x minus 0 to the nth. And again, you could make this from 0, and that is exactly the series that we thought turned out to be e to the x. You can either write it like this, and then this is important enough that I'm going to rewrite it as the way you often see it. Even though it's nice to put the c sub n's out front, this is a nice compact way to do it. And then write it out with some of the terms to show what they look like. So we have our first Taylor series, although we kind of found it before and just called it a power series. Because a Taylor series is a power series, a special one. Now you might want to say, what's the purpose of having this? Why am I so excited about this? Well, in general, there's a lot of things, especially when you start to get into higher physics and that, where you want to take complicated transcendental type functions like e to the x and then trigonometric functions like the sine of x and write them as polynomials. And you don't have to have them perfect, so you could just use a Taylor polynomial to approximate it. But even another thing, if you think about every time that you type on your calculator and you type, say, you want to take e to the 1.237 power, how do you think a calculator knows that? There's an infinite number of real numbers you could put as an exponent. And there's no way a calculator could just have those all stored. So you can see a calculator can store a lot of terms of e to the x's Taylor series, and then just plug 1.237 into those, and that's a calculation that a calculator can do. So there's just one example why you might want to have a function like e to the x represented as a polynomial. And what's the good thing about this? We've already done a test to see where this converges, and it ended up converging for all real numbers. So that even makes it more valuable, because I could even take e to the 100th power. Now, what's going to be really important is this remainder. So I'm going to tell you what our n of x is. It's the n plus first derivative. In other words, if you use n terms, or you take an nth degree Taylor polynomial, the error is going to be found by taking the n plus first derivative at c. and dividing it by n plus 1 factorial times x minus a to the n plus first power. That's exactly the error that you would get, what you'd be missing. And c is between the value of x that you're plugging in there and the center. So this is the Taylor remainder. The trouble is we never really quite know what c is. Now I'm not going to prove this. This is a really complicated proof, but I do want to show you where the c comes from. So I'm going to prove it just for the simplest case. What if you have f of x and you're going to use a 0th degree Taylor polynomial? So that means you're only going to use the first term plus r0 of x. So that would be what you get if you took the most simple Taylor polynomial for f of x. Now, if you take like y equals f of x, and you take a point right here, A, and then you were approximating y equals f of x with y equals f of A. So that would just be this horizontal line right there. So what if we then plugged in the value x? The error that we're going to get is right here. So what do we know by the mean value theorem? That if I take that slope right there, there's going to be some point x equals c where you have that f prime of c equals the rise over the run. So f of x minus f of a over x minus a. So just by manipulating this a little bit, you get f of x equals f of a plus f prime of c times, and I'll put it over 1 factorial times x minus a to the first. And I think you can see that that's exactly what Taylor's remainder is saying. If we're using a 0th degree Taylor polynomial, the next derivative would be the first derivative at c divided by 1 factorial times x minus a to the first. And c would be between what? Between x and a. Somewhere between x and a. So there's a proof of Taylor's remainder using the simplest case. And then one other quick thing that I wanted to show you. What would happen if you use a first degree Taylor polynomial? Then what do you have? You would say f of x equals f of a plus f prime of a times x minus a. Or just rewriting it a little bit, you have f of x minus f of a equals f prime of a times x minus a. Y minus the y value equals the slope times x minus the x value. What we find is that's just a tangent line. And to think about it, doesn't that make a lot of sense? If you had some function and you were trying to approximate it really well near x equals a, isn't the best straight line that we could approximate it with a tangent line? So all of this is kind of fitting together. Okay, so let's proceed over to this problem. So pretend that you are inside a TI-84 calculator. And a student types in on your calculator the sign of 3, which you don't have stored. So what you're going to do is use a Taylor polynomial for the sign of x to approximate the sign of 3. And you have to be confident in the answer you display to the student. So the question is, should you use, oh, and here's a term I haven't said what it is yet, but I'll tell you really soon. A Maclaurin polynomial of degree 11 or a Taylor polynomial centered at pi of degree 3. Well, a Maclaurin polynomial is really, another way of saying that is a Taylor polynomial centered at 0. So a special name is given to a Taylor polynomial when it's centered at 0. It's called a Maclaurin polynomial, after a Scottish mathematician called Colin Maclaurin. He was a child prodigy, the youngest professor of mathematics ever at age 19 at a university. And he didn't get his name put on that just by putting 0 in for A. That would be too easy. He worked along with Blake Taylor on these Taylor polynomials, and so he was given that name in his honor. So the question is, what should we do? Should we center it at 0, or should we center it at pi? And why would we pick pi? Because that's a value of the sign that we all know, and pi is pretty close to 3. And we see these Taylor polynomials do better when they're close to their center. So why would you ever go with just a regular Maclaurin polynomial? They're just easier to do when you're plugging in 0. So let's look at the choices. So in both cases, we're going to start with the sign of x. So the derivative is cosine of x minus sine of x minus cosine of x. Then you're back to the sine of x. And it's going to kind of go into a repetitive cycle here. But we don't really need f of x, we need f of a. Well, this time, since it's a Maclaurin polynomial, it's centered at 0. So f of 0 is the sine of 0, or 0. F prime of 0 is the cosine of 0. F double prime is back to 0. The third derivative is -1. The fourth derivative is 0. And the fifth derivative is back to 1. So if we wanted to write the series for the sine of x, what do we get? The first term is f of a, 0, and then it goes plus f prime of a over 1 factorial times x minus 0 to the first. Then it's plus f double prime, 0 over 2 factorial. Well, I don't even have to write that down. Then it's going to go to the third one, plus a -1 over 3 factorial times x minus 0, and I'll just put x cubed, and then it's going to skip the fourth because it's 0, and then you're going to be back to 1 again, plus 1 over 5 factorial times x to the fifth, and then it just keeps going. So we can write this, the sine of x, simply is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And I think you can see the pattern there. So because it's a pattern, you can also write that as a summation. So you know that it alternates. So you have -1 to the n, or to the n plus 1. I'm never too sure, so I'm just going to put that there. And times what? Well, these skip. They go from 1 to 3 to 5, so we're going to have x to the 2n or 2n plus 1. You're never too sure, and then you're dividing by the same thing. Factorial. Well, then try it. At n equals 0, you get x to the 0 power. Well, you don't want x to the 0 power, so you could put plus 1. And you want that first term to be positive, so you do want to have it at n. So we've got a Maclaurin series, a Taylor series centered at 0 for the function the sine of x. That's going to be really valuable. So now what could I do? I could now say the sine of 3 is approximately equal to, and we can use as many terms as I want. Well, we're going to try 11th degree Taylor polynomial, which means I have to go n equals 0 to 5 to get up to x to the 11th. Now you could do this out by hand, but there is on your calculator a way of doing these summations. So I did it ahead of time, and it comes out to be 0.1408746. That's your approximation for the sine of 3. The question is, you want to know, do I feel confident to put this out on my student's calculator? So what I notice is this is an alternating series. So I can say the error in absolute value is less than the absolute value of the first term you omit. Well, if I go up to x to the 11th, the first term I'm going to omit is to the 13th power. So, and it's going to be 3 to the 13th divided by 13 factorial. By the way, this x here really should be a 3 because we're going to put 3 in for x to get that. And this error turned out to be 0.00024. So our error bound tells us that the error is less than 0.00024. So we're feeling pretty good about it, but not great, because on the calculator they use more digits than that. So we're actually going to have something that isn't going to be that right for the student, even though we used up to x to the 11th power terms. Now, just to show you how good the error bound is, the actual sine of 3 is 0.1411208. And if I take this minus this, I get 0.00025. So what you find out is that error bound did a pretty good job. It said the error was less. Oh, let's see. Yeah, that doesn't seem quite right. But anyway, it came out very, very close. Maybe I'm off by a digit there. But you can see that the error bound versus the actual error is very, very close. But still, you're going to have an error. If you wrote that, and that's the real sine of 3, your student might not be too happy. So let's see what happens if we go to a Taylor polynomial centered at pi. We're still going to get these same derivatives. So we don't have to change that. We just have to plug in, instead of 0, we plug in pi. So f of pi is the sine of pi, which is still 0. F prime of pi is the cosine of pi, which is -1. Then we get that back to 0. And now for the third derivative, we have minus the cosine of pi, which is 1. So we're only going to a third degree Taylor polynomial. So we can say the sine of x is approximately equal to, and the first term would be 0, and then we go minus 1 over 1 factorial times x minus pi to the first. And then we'd have another 0 for the second power, and then we're back to 1 again. So we have plus 1 over 3 factorial times x minus pi cubed. So that would be the third degree. This would be P3 of x. And if I wanted to then approximate what the sine of 3 should be, all I have to do is put 3 into this. 3 minus pi plus 1 over 6 times 3 minus pi cubed. So you don't even really need to put that in the summation. As it turned out, that turned out to be 0.1411193. You can see closer to the actual sine of 3. But if we didn't know that, and we had to predict how good this is, again, this turns out to be an alternating series, so we could use the alternating series test. But I want you to get used to the Taylor remainder test. So what did we say? If we use this as P3 of x, what is the remainder? The remainder would be R3 of x, which uses the next derivative. Centered at C over 4 factorial times x minus the center to the 4th power. And what do we know about C? C is between the number we're plugging in, 3, and, well, I'll just put x and pi. And we're going to use this at x equals 3. So we can say it's the 4th derivative at C. Well, what is the 4th derivative? It's the sine. So it would be the sine of C over 4 factorial times 3 minus pi to the 4th. And the thing about it is we never really can find out what C is. We just know it's somewhere in between. It's sort of like, it's because of that mean value theorem. So what we do is we put an error bound. This is the exact error. But we can say as an error bound that it's less than. We know that C is between 3 and pi. And the sine of pi is 0. So the worst possible case would be at the sine of 3. But we don't know what that is. That's what we're trying to find. So at least we can say the sine function never gets bigger than 1. So we know if we put a 1 here, what we put here as our bound is going to be bigger than the actual error, and that's what we're doing. We're finding an error bound. So we can go 1 over 4 factorial times 3 minus pi to the 4th. And that turns out to be 0.0000167. And you have to realize, I mean, I could say the error is less than 1 billion, and I'd probably be right almost every time. But you want a bound that gives you confidence. If I just said the error is less than 1 billion, you wouldn't be very confident. But when I say the error is less than this, we're pretty confident that the answer that we got here is pretty good. And I'm even going to go one step further. This is a little bit of a subtlety, but you might as well learn it now. Because the next derivative would be 0, P3 of x is the exact same thing as P4 of x. Because if I added and made that P4 of x, you'd just get x minus pi to the 4th, but it would be 0. So since Taylor's remainder works for P4 of x, I could say that R4 of x would be, now we would go to the 5th derivative at c. So it would be the cosine of c over 5 factorial times 3 minus pi to the 5th. And by the way, I probably should have put that in absolute value. When we're looking for errors, we're looking for the magnitude, so we don't really care whether it's positive or negative. So we can now say our error is less than, and the cosine of c is going to be the biggest at pi, because we still know that our c is between 3 and pi. So the highest magnitude of that would be 1. So we have 1 over 5 factorial times 3 minus pi to the 5th, which turns out to be our error is less than 0.000000474. And now I would feel much more comfortable typing that out on the calculator display because it's so close to the actual. And you can see that it is really, really close to the actual. The actual error is 0.000000470. And we know the error is less than that. So again, we had a really good error bound. And you learned a little bit how to do these types of error bounds, which, by the way, I should tell you what the name of this error bound is. The actual error is called a Taylor remainder error, but the error bound is named after a French mathematician called Joseph Louis Lagrange. And so this is called the Lagrange error bound, because he used a lot of Taylor and Maclaurin's work and used these error bounds to be approximating a lot of functions. So this is called the Lagrange error bound. Now, since this was really important, we came up with another really important Taylor polynomial. I think it's important to see where this converges, because if it doesn't converge for many values of x, it's not so valuable. So this is, again, good review. How do we find out where one of these power series converges? We use the ratio test on the absolute value, because we're going to find out where it converges absolutely. So what we have to do is take this and go x to the n plus 1. Well, if I put n plus 1 in for n, I get 2n 2 times n plus 1 plus 1 divided by, and that's going to be 2n plus 3. So I go 2n plus 3 factorial, and then you divide it by this term. So you get 2n plus 1 factorial over x to the 2n plus 1. And you can take out a x squared. X to the 2n plus 3 over x to the 2n plus 1 is x squared. And you have the limit as n approaches infinity. 2n plus 1 factorial over 2n plus 3 is 1 over 2n plus 3 times 2n plus 2. And where is this less than 1? Well, as n approaches infinity, no matter what you put over here, we can make this small enough that the whole thing is going to be less than 1. So, good news again. This converges for all real numbers. So this becomes a really important Taylor series, just like the one for e to the x. And I guess we've done an awful lot today, but we've still got a little bit more board space. And I think this really is tying a lot of things together. How could we get the cosine of x? Well, we could do that the same way we did here. But what do we know? We know with the cosine is the derivative of the sine. So all we can say is the cosine of x we can get by taking the derivative of here. So you get 1 minus, and it would be 3 times 1/6. So you would have x squared over 2 factorial. And then you'd go plus, and now this becomes 5x to the 4th over 5 factorial. So it becomes x to the 4th over 4 factorial. And if you wanted to write it in summation form, again, it's alternating and it's skipping. So you would get this. When n is 0, you get 1. X to the 0 is 1 over 0 factorial. So that gives us 1. When n is 1, you get a negative x squared over 2 factorial. And you can see that that summation is the same thing as what's up here. So now we've got another extremely important Taylor series. And you could have gotten this by just taking the derivative of this with inside the summation also. But I think we've learned enough for today. Taylor series is considered one of the more important things that you learn in a Calculus 2 class. And it takes a little while to really get used to them. So if you feel a little overwhelmed, don't worry. We're going to do more. We're not going on to the next topic. We're going to do more on Taylor series in the next video, and maybe even a third one. So, you take care.